Okay, so welcome to the final video of the video tutorials. So in this one we're going to apply the third eigenanalysis that we've learnt about, and that's the eigenmode solution with the K and the M matrices. So quite similar obviously to the previous eigen analyses that we've done. So for that reason I'm going to do Control C and Control V, but we do need some slightly different information coming in here. So actually for the mass matrix I don't need to have the Young's modulus. What I do need instead is the rho value, so that's the density value that we'll come back to talk about in a second. So I'm just going to, we'll connect in when we need to there. And I don't need the change in length either, so that will obviously cause an issue straight away. And that's because we've got the wrong Python script in here. So what I'll do is I will just open this up, Control A, and then just delete everything in there. And then the final Python script that I want says this K and M eigenanalysis. Very similar, we're just constructing the mass matrix in here, and you can see the row information, so the density information that we need there. So I'll do Control A to select everything, Control C to copy it, and then going back into my Python within the Grasshopper, Control V there. So we have everything coming in like so. I'll just save that. And of course at the moment it's just showing that error because it doesn't yet have the density information. So for the density, we obviously can specify this in whatever way we want. I'm going to take the value for steel, and I'm doing this, so just set this to multi-line data as usual. I'm doing this for a unit that I've decided to use, which is milligrams per millimeter cubed. Okay, so obviously normally you probably would find density for something like steel quoted in kilograms per meter cubed. We're just initially taking the value in milligrams per millimeter cubed. But I need, if you read through the notes, I need to convert this, if we've been using newtons and millimeters all the way along, I need to convert this into a slightly unusual sounding unit. So I need to convert it into tons, and we're using metric tons per millimeter cubed. So a ton is 1,000 kilograms in the metric system. Okay, so I'm going to use that with an expression component. And obviously I'm just converting here. So in order to do that conversion, it's the x, the value that I've put in, times 10 to the minus 9. We will just group this here so that it can add a title, and we'll note that this is converting to tons per millimeter cubed, like so. So the reason that it's to the minus 9 is obviously milligrams to grams would be 10 to the minus 3, then grams to kilograms is another 10 to the minus 3, and then finally kilograms to tons is another 10 to the minus 3. So we can feed this in now for the row. So we'll just check what might be going on here. So this doesn't require list access, this is just item access. So we now have all of that sorted out. So obviously the final thing then is I can just bring down this. So Control C, Control V, bringing all of that information down, and it's the eigenvectors from here that I want to feed in. But actually there is one final little bit of processing that goes on within this Python script, and that is, as well as the eigenvalues, I've actually done the conversion within the Python script, so we can get out frequencies, and these will be in hertz. So just Control C, Control V there, and I'll just tidy all of this up a tiny bit. Okay. So from here, I can just bring my panel components. So we've got the eigenvalues is one set of data, obviously. I'll just move everything down a little bit. Bring my density down, and then another panel for the frequencies. So I can bring them across like so. So we are still using the column. So I'll just show that like so. We can run through the eigenmodes, so you can see these are quite similar to some of the buckling modes. But now these correspond, so obviously just got something not coming out quite right there. Let me just see, so that should be a float coming out for the frequencies. So you can now see these are the frequencies, and obviously what we would do is we'd look to avoid frequencies that might be occurring within the loading, but we could also use this system to allow us to assign additional masses at the design stage if we wanted to avoid certain frequencies, or obviously in the design of tuned mass dampers. So we have everything there. If we did just want to check some values, for example, might go back here. So I could just turn this into either a simply supported beam or a cantilever. So if we turn it back into simply supported beam, remembering it really doesn't matter what the loading is. So in this case, we'll have a cantilever when we're doing our frequency analysis, that is. So here, again, we have the modes that we would expect. We can just cycle through them quite easily. If you want to get an idea of how the actual sort of vibration might work, or how it would look, obviously we can run through the relative magnification. So that kind of gives you an idea of how your structure would be oscillating. So we can just go back here. So although the cantilever is the very commonly chosen example, we can do a simply supported beam as well. So just restricting in the y-axis there, obviously removing the rotational constraint. So we come back down here, so we've got our original elements and our eigenvector elements, and again this is sort of showing what we would expect. So that's the first mode, or the zero eigenmode as we're calling it, second, third, fourth, fifth, and so on. And you can see, as we would expect, that obviously the frequencies are increasing for each mode. So there we have it. Essentially, I hope, although obviously some of the wiring is beginning to look a little bit like spaghetti by the end of all of this, but we have various Grasshopper definitions that allow you to do everything really that you might want to do with the stiffness method, and I hope you found the Eigenanalysis useful as well. I'm sure you will refer back to this in future work, so it's, I hope, a very useful digital tool for you to have. So I will just show the eigenmode for the final time, and then we can zoom out and just get an overview of everything there. So thank you very much, and I look forward to discussing the coursework with you. Okay, cheers.